Morning. I already started recording. How are you doing? We are close to. We are getting close to the exam. So. A reminder, we have lecture today and next Monday. The calendar is here. Nothing changed, just a reminder. Next Monday, I scheduled 4 hours, meaning that we will stay in the room for 3 hours up to noon, and then a little bit less than noon. Okay, and then we take a coffee and we go to the lab. Of course, the visit to the lab is optional. There is nothing there that is relevant, I mean, for the exam. Absolutely not. But it's a nice visit. It will take less than 1 hour. And if you have other commitments, because I am aware that I am exceeding the time of our scheduled lectures, it's no problem at all. It's just an opportunity for you. But before going there, between 9 and 12, I plan to lecture and to make at the end, so before noon, a recap of everything. And I will also open the floor to question and answers. And if you don't have any question, it's no problem. And we stop maybe earlier, but I hope that you will have several questions. So that's it. And there are also here some more links for exercises. I'm not sure we will have time to make the last exercise. So in the same way, I'm not sure we will have time to make the last lecture, Design of Climate Change Adaptation Actions. It's not really relevant. Even last year, I didn't go through it. And of course, what is relevant for you for the exam is what we did here in the room. So any link that we skip, it's not relevant for the exam. I leave the link there because indeed it is also something that may be useful to you later if you wish to expand. And also the links that I'm skipping, I think that they are also prone to self-education, to self-study. So I will leave the links there, but of course, when I make the recap, I will summarize next Monday what are the links in this list that are relevant, okay? Good. Any question? Okay. One announcement, which is actually not relevant to you, but I would like to rely on your network for giving visibility to this webinar. It's not relevant to you because we decided to activate for the next year for the master degree program in civil engineering 2 more curricula, and one is focusing on climate change adaptation. So one of the exams, of course, will be climate change adaptation that I'm teaching here. Not really the same because this curricula is to be held for the second year in Ravenna. But I'm showing this to you because if you have any network of interested students, of course, bachelor students in your country or your, I would appreciate your cooperation in giving visibility to the webinar that we organize next Monday. Actually, I see the timing is, I'm noticing that the timing is conflicting with our visit in the lab. So I will need to make a change in our schedule, and I'll make it soon, okay? I'm sorry for this. I really noticed that because they scheduled the webinar for me and they didn't know. I didn't tell them that I was planning to go in the lab from 12 p.m. to 1 p.m. So first, let me close this. And so if you have any network to advertise this event, it is on my website at the top. So this is my website, actually. I really would appreciate your cooperation. Okay, close this topic. Now let me go back a little bit with the schedule for next Monday. We need to change, anticipate 1 hour everything. Okay, is it clear? So we stick on our 3 hours for lecturing. So we will move to the lab at 11, not 12. Okay, everything is clear? Perfect. So no problem at all. I just noticed that the clash. Okay, good. Any question? Perfect. Now, let me move to our lecture dedicated to decision theory. I'm not using Chrome because I don't know why. There are some symbols that in this lecture that appear in Chrome that don't appear in Firefox. The symbols actually are nothing wrong. So, but just to give you an example, sometimes I experience only on some PCs some visualization problems, like this symbol here. You see this square? It shouldn't be there, and I don't understand why it's there. It's not implying any other mistake in the equation. It's just something that I don't understand why it shows up. So let me move to Firefox because in Firefox there are no problems. And this is the lecture under Firefox. Anyway, if you see some visualization problems, usually they are like squares or things like this that should be just blank. And they are not changing, they are not implying a real mistake. It's just something that shouldn't appear and it's there. So no problem at all. Okay, so as I said, I would like to focus on decision making to close this course. Why decision making? Because decision making in the presence of climate change is something that is really relevant, and decision making decisions or the challenge of taking a decision for acting against climate change is very often the reason why we don't do anything. Like, for instance, I am frequently asked the question, are we doing something relevant in the Emilia-Romagna region to avoid that a flood like the one that occurred just 1 year ago, by the way, it was May 18, is not repeated in the future? And it's not an easy question to answer because actually I think that we are doing something, but the problem is that in the presence of uncertainty, we are not sure what is the best option. Okay, so what is the best option to reduce CO2 emissions, or the best option is to make detention basins, or the best option is to avoid that that animals undermine the stability of the levees? Actually, there are uncertainties on the causes of the events, and taking decisions in the presence of uncertainty is a problem because we have not unlimited resources, especially in a country like Italy that has a large public debt. We don't have enough resources for doing everything. And also, we are not exposed only to flood risk. We are exposed to drought risk, to earthquake risk, to volcanic risk, not in the Emilia-Romagna region, or let's say, not really. It's not really likely in the Emilia-Romagna region. And so we are exposed to several risks. And of course, we need the resources to get protected. And the resources in Italy are limited for the large public debt. And therefore, you know, to decide what is the best option in the presence of uncertainty, if there was no uncertainty, it wouldn't be a problem. Because we would be sure that the solution is a given one, and we would be able to go with that solution. But in the presence of uncertainty, we have several alternatives. So taking decisions under uncertainty is a challenge. And it's a challenge, especially when you deal with a problem that has a relevant societal implications, of course, and it's relevant for the life of people. It's relevant for also for the wealth in general and the welfare of the community and the country. Actually, we are well used to take decisions under uncertainty. And I mentioned several times, we take decisions under uncertainty every day in our everyday life. And usually we are used to take these decisions based on heuristic approaches. What does heuristic mean? It means that we decide basing on some rules of thumb which derive from our experience. Heuristic means something based on common practice, on personal experience, something that is not theoretically based. So there is no analytical theory supporting an heuristic approach. The heuristic approach derives from experience. So, I mean, we look at the weather, and basing on our experience, we decide whether it's likely that today will rain or not. And therefore, we decided whether it's the case of taking an umbrella or not. And this is typically heuristic. If you look at the weather forecast, it's not an heuristic approach, because the weather forecast is based on an analytical model which derives a forecast of the weather. And then this is something that is based on a theory, on a rigorous approach. Sometimes you know that the heuristic approach is better, is safer, is less uncertain than a rigorous approach. It may be the case, okay? It may be the case. But so this is why heuristic approaches are widely used, especially when it's just a matter of a personal decision, because very often the heuristic approach is subjective. It's something that depends on your perception, on your experience. So you understand that when a problem is societally very relevant, it's not easy to take an heuristic approach, because it's also a political decision. Political because it implies the use of a public resource. So anytime that you use public resources for putting together a strategy, realizing a strategy, it's a political decision. And political decisions, you know, for obvious reasons, sometimes, you know, deciding based on heuristic approaches is not a good thing, especially in a democratic system, and especially today where we have a strong belief in the value of transparency, in the value of collective decisions, in the value of grassroots decisions based on the opinion of people, which is for sure a very relevant value. On the other hand, you understand that you cannot convene an assembly of people and say, I think that in the Romagna region, we have to realize detention bases because it's my feeling that this is the best option. And, you know, these people would probably ask questions like, okay, but why best option? And then you have to explain. And if it's just your belief, it's a problem. So you need a rigorous approach. You need something more convincing, more analytical. On the other hand, you need something simple to explain, because if you show a slide, a sequence of slides with a lot of equations, like I will do today with you, it's not very convincing, okay? Because, you know, people get lost. So basing on the audience, you have also to adopt a transparent approach, where transparency means also that the approach is understandable. So this is why decision theory in the past, let's say after the Second World War, became so popular, because people understood that, you know, there was a push for democracy, a push for transparency, and because we recognized the great value of involving communities in taking decisions regarding public goods. And therefore, also people recognized that it was important that the decisions were taken in a transparent and rigorous way. There is also to say that decision theory was much stimulated after the Second World War, because during the Second World War, really, decision theory was born and widely used to manage the strategies during the Second World War. And so this is why there was also a crossing of several drivers that stimulated this new science. This science was developed in several different fields, and at the beginning, before I move forward, let me make a premise, okay? And showing you a slide, which should be okay, down here, a sketch, before moving forward. And it's the difference that I already mentioned between a top-down approach and a bottom-up approach. And you can get an interpretation of this of these two categories. So you still don't have the basis for understanding this figure, but you can understand the meaning, the general meaning, which I am explaining now to you. Look at the left column. This is a top-down approach. Top-down means decision taken from the top of the hierarchy, and the top of the hierarchy can be either an interpretation, a political interpretation, like the decision is taken by the government, full stop, or in the past, the king or the dictator, whatever, decides, okay? And then the decision is taken. In a more scientific context related to climate change, top-down, we usually mean that we start from climate, and from climate, we identify risks, design variables, and then basing on the design variables like earthquake intensity, expected earthquake intensity, then we decide a set of strategies to address the related vulnerabilities. I made the example of the earthquake because I think it is significant. Let's suppose that we have an earthquake model. Actually, we are trying to set up earthquake models, but you know that there is a lot of uncertainty. We are still not able to predict earthquakes, and we are still not able to predict the probability associated to an earthquake of a given intensity in the future. But let's suppose that people decide anyway to use current models to estimate the risk of earthquakes, and then they estimate the design variables for the buildings, for the infrastructure, for the bridges, for the dams, and then you end up with a design variable, and you design the bridge, the building, basing on the design variable, which is derived from the earthquake model. You understand that this procedure, for the case of the earthquake, is not really satisfying because, I mean, it's so uncertain, the earthquake model, that you end up with something, with the strategy that we are not sure that is effective. So this is the scientific interpretation of top-down. Top-down was largely used in the past, especially with the climate change analysis. So climate scenarios, design variables, strategies. Today, with the advent of the concept that the community needs to be involved, we tried to reverse this workflow. So we start from the problem. Okay, so we start from either candidate strategies or vulnerabilities. So we start from the problem, and we start from what is possible. So strategies, meaning that what can I indeed make? What resources I have to make things, and then I identify the strategies. And then we evaluate these assessments of strategies or vulnerabilities basing on the climate scenarios. And we identify those scenarios where the strategy is ineffective. So if we see that the strategy is ineffective or the vulnerability is there only for few scenarios predicted by the models, then we may say, okay, the strategy is effective for 90% of the scenarios. That's fine, okay? And this is the bottom up. So transparency, involving communities, also we believe that implies the bottom up approach, which is very recent. And the bottom up approach is a concept that was launched like 20 years ago. So let's start not from the top, but from the bottom. What is the problem? What are the vulnerabilities? What are the possible strategies? And of course, there is a difference between starting from the strategies or starting from the vulnerabilities. But let's start from the current problems. So we are sure that at least we do something. Okay, this is my premise. Now we can start again from the beginning, and I use a PowerPoint. Okay, so first of all, what you see in this figure is really interesting. You can see in Wikipedia, this is the nilometer. The nilometer, I think, may be a nice example of a very ancient decision-making, decision support system. The nilometer, this is a staff. When the level of the Nile River goes up, the water climbs along the staff So people every year, because they were interested in the max level every year. So every year they went down along the stair and marked on the stuff the max level of the current year. And then they cleaned up the stuff. Because the Nile River during floods is muddy, the water is muddy. And therefore, the max level was recorded every year. So at the end of the year, the Egyptians went there, put a mark and cleaned the stuff. And this is something really, in my view, it's amazing, astonishing. 3,000 years ago, okay? And basing on this sequence of marks, they tried to predict for the next year what was likely. And therefore, they tried to understand the regularities, like try to understand whether there were cycles to make a prediction. So this is the first example of a decision support system, I think, heuristic, because they didn't have a theory, but still based on observations. So let's skip this because I already made the introduction, okay? And now, decision theory, as I said, was developed in several disciplines. I will make reference to water resources management, floods and droughts because of my sympathy for this topic, but actually decision theory was developed also in finance, in economics, in the military fields, several of them. And at the origin, people start with the very simple idea of seeking optimality. Seeking optimality like we did for our exercises, estimating the parameter of the linear reservoir model. We sought optimality, okay? So objective function was defined like an economic benefit or like a risk equation. And they tried to seek the optimum of the risk equation, like minimum risk, seek the optimum of least squares or economic benefit or whatever, okay? And there was a lot of history related to optimality, perfect. But then people realized that in the presence of uncertainty, optimality has some downsides because, they realized that an optimal strategy may dramatically fail even with a small amount of uncertainty. So it may be that if you take your data for granted, like we did for the linear reservoir, okay, what we did is in our exercise to take some flow data and we took them for granted, no uncertainty, okay? And then we estimate the parameter of the linear reservoir and we got quite a good performance. You may remember that I said, this is too good. It was almost perfect, okay? People realize that if you perturb your data, even of a small amount, what is a perfect simulation may turn out into a dramatically wrong simulation. So they realized that optimality was not really reassuring because even for a small amount of uncertainty, they realized that some optimal solutions dramatically failed. So people understood that it is, especially when dealing with climate change, with natural disasters, people understood that it may be preferable a solution that is not optimal, but is robust. And I already gave the definition of robust to you. Doesn't dramatically fail in the presence of uncertainty. And so they started seeking robust solutions. What is an example of a robust solution? An example may be what is called robust optimality. And let me give you an example on the blackboard, and let me just change the camera. A very simple example. Okay. Here it is. Okay. So let's suppose that we have two alternatives for a decision to be checked, to be selected against two climate scenarios. So let's create a table with alternative A, alternative B. Okay, it's a very generic example. And let's verify these two alternatives against two climate scenarios. So scenario 1 and scenario 2. And let's suppose that we have a performance measure, okay? Scenario 2. Okay, so let's refer to scenario 1. And we estimate that alternative A has a benefit of 5, has a performance of 5. Let's keep it very generic, okay? We don't define what is the performance measure, if it's the number of saved people or it's an economic benefit. And alternative B has a benefit of 4. Good. So if we had no uncertainty, only scenario 1, no uncertainty means that my climate is sure. I have only one scenario. I would select, of course, this one. But in the presence of uncertainty, I may end up with another performance here, which is, again, 4 here. And here I have 2. Okay? So in a robust setting, people may prefer then alternative B. Because alternative A, in the presence of uncertainty, is the best one. On the other hand, I can get the lowest minimum. And here, the performance is not the best one, but still, if scenario 2 materializes, I have still a satisfactory performance. So, depending on what is your performance measure, and depending on your propension to take a risk, I think, for instance, if this is the number of saved people, so something really relevant, you would prefer probably this one because, okay, here you may save one more person, but you may lose 2 more persons if scenario 2 materializes. So probably depending on the context, this could be considered this is for sure the more robust solution. Okay, more robust. So more robust. And what I applied here is optimality with respect to the maximum of the minimum. This is also called max-min method. Max-min method. You can call it also min-max. It depends on if you seek the maximum of a performance measure or the minimum. If you use least squares, you look for the minimum. So, I mean, max-min can become min-max. And this is a case of robust optimization. Robust optimization. Of course, you can decide with another method rather than the max-min. You could have probabilities related to scenario 1 and scenario 2, and therefore to take a weighted measure. And so there are alternatives to max-min. In this case, I just look at the possibility of these two scenarios without taking into account their probability. But of course, if I am told that this is associated to a probability of 99% and this is associated to a probability of 1%, I may decide I may conclude that it's more robust scenario 1, scenario A. Okay, sorry, solution A. Okay, and but if I just look at the possibility, the max-min method is an example of robust optimization. Robust optimization is larger than the max-min method. but it is a nice example. And this is the first development. People looked at the worst outcome. But you may understand a couple of things. First of all, in decision making, but in general, in our life, and one second, and let me look at the next slide. Yeah, this is the proper slide to put on the screen. And there is no the example in the slides. The example is only in the blackboard, but this is the right slide. In our everyday life and in politics, seeking making strategies, seeking decisions basing on the worst outcome may turn out to be not efficient, too prudent. Sometimes we need to accept a risk because it may be too conservative to seek the maximum of the minimum benefit. It means that we lose opportunities. And, in planning societal development, it is extremely important that we also benefit from opportunities. So it may be worth taking a risk. If you look at the history of human development, humans always took some risks to support their evolution. And so people realize that this solution of robust optimization may lead to losing opportunities. And keep in mind this concept of opportunities that we don't have to ignore, because otherwise we slow down everything in terms of societal development, in terms of welfare. And also related to climate change, I think the concept of opportunity is extremely important. We don't have to forget the opportunities that climate change may deliver. Of course, we have to compare them with the problems originated by climate change, but taking into account the opportunities has been the motivation for seeking a step further beyond robust optimization. Now, I want to give you a couple of examples of robust method for decision making. A couple of more examples, which I selected from the many ones that you can find in the literature. And actually, I will give you 3 examples, but only one of them will be investigated with some detail, discussed with some detail, starting today. And the reason why only one of them is investigated with more detail is precisely the fact that, as you will see, the one that I am discussing with more detail is the one that also looks for opportunities. The other 2 methods, I will introduce them to you with less details. Okay, so let me start with the first one, which is the one that I'm not describing with a lot of details. And note that, so I will give you 3 examples, and I already discussed robust optimizations, so it's a 4th example. These methods have some intersection. And some intersection because, of course, at the end of the story, you have to get an idea decision, and they more or less have to give this comparable results, very close results, okay? And therefore, of course, they have some intersection. So, for instance, the max-min can be a special case of the method that I am describing next, which is called robust decision-making, okay? And robust decision-making, as I said, I will not go into the details. Before I move forward, robust decision methods are normally classified as bottom-up approaches. Why? Because when you seek robustness, basically it is implicit that you also look at the effectiveness of what you are planning. So you look at the results, and if you see that a decision is not robust, it means that after checking, sorry, I forgot to shut up the phone. I'm sorry. Usually I don't get many calls, so this is why I forget to. Okay, good. So usually they are classified as bottom-up approaches, and in particular this one, because you will see that there is a starting point that starts from strategies. And by the way, robust decision making is one of the methods which I included in the graph that I showed you before. So what does robust decision making do? I'm giving a narrative explanation. And narrative explanation means that you don't have about these methods to remember any particular equation, but try to just look at the concept, okay? And first, we start with multiple scenarios of the future. So indeed, we start with, in the frame of climate change, in the framework of climate change, we may start with climate scenarios, okay? And which may give the feeling that it's a top-down approach, but actually it is not. I will explain you in a moment. So, and these scenarios are considered without looking at their probability, but just looking at their possibility, okay? Possibility means, okay, a scenario may happen. So I'm not interested in the probability of it happening for now, okay? And this decision of not looking at the probabilities at the beginning is taken in order to make sure that we are transparent. Because, you know, if you tell people, the scenario, yeah, it's possible, but it's very unlikely. So people may think something like, why it's unlikely? Because if it is a scenario that for people is very relevant, like if a person has an house just at the bottom of a dam, and you say it is very unlikely that the dam collapses, but the person may think something like, okay, but if it happens, it's me. So, I mean, it is, there is a say which says, nobody's interested in the very unlikely event, but the persons that are hit by the event, even if it's unlikely, okay? So think of Damocles, you know, he was the one that was hitting in the banquet just under a sword. So it was very unlikely that the wire broke, but he decided to leave it because when it's you. So, I mean, when you talk about probability, is already something that is obscure, while possibility is clearer. So this is why they decided in this method to look at the beginning just at the possibility of scenarios. Okay, perfect. And then you look at the consequences of the scenarios with some performance measure. Like, for instance, you take a flood model and you estimate the damage caused by the flood. And then you identify the strategies. So how can I cope with this scenario? And then actually, this is the starting point of the procedure. So strategies. I look at the strategies, okay? And then once I identify the strategies, I check what are the scenarios under which the strategies are effective and what are the scenarios under which the strategies are failing. So there is a travel back, a way back to the scenarios after the identification of the possible strategies. Okay, so you understand that it's quite different with respect to using a scenario design variable and then designing a strategy. I use the scenario design variable and then I see what strategies are possible. What strategies are possible? Can I build a dam? No. Okay, let's forget it. Can I reinforce the levees? Yes. Okay, let's consider reinforcing the levees. And then I go back to the scenarios and I see, okay, if I reinforce the levees, 8 scenarios are solved, 2 scenarios are still dramatic. Okay, so you go back and this is the last bullet item, vulnerability and response option. Okay, and then based on the analysis of the scenarios, you can come back again to the strategies and say, okay, how can I modify the strategy in order maybe to add one more scenario to the list of the solved one? So there is a back and forth where, okay, the climate scenarios are the starting point, but they are not used for design. They are used for verification. And this is what makes the approach bottom-up. Is the concept clear? Do you have any question? And I'm not giving any example of models that can be used to evaluate the performance of the strategies. I'm not giving any analytical example. It's just enough for me for now that you understand the concept. And if you don't have any question, I make a scheme of how this can work. And let me skip this because I already discussed the content of the slide, and everything is reported in the web pages, okay? Okay, so step 1. If you have any questions, stop me, okay? No questions. Let me unpin the blackboard. I don't really know what is the effect of unpinning the camera with when the screen is shared, but some students told me that it's better when I go to the blackboard that I pin the camera. So step 1, identification of future scenarios. Typically in our context, we use climate models, and I'm not looking at the probabilities, so that's fine. Just I use several models, several initial conditions, several scenarios, and because you know that probabilities of climate scenarios are an open question, an open challenge, okay? And then I need to identify the metrics to evaluate performance. So, we need, this is an important discussion with the stakeholders. This is already a bottom-up approach. So what kind of measure do we use? Economic benefit rather than number of people who die or number of people who are injured? So what is the performance measure? And I anticipate that now I'm focusing on a single performance measure, but there might be the case where you have many. So you're interested, yes, in the economic benefit, but also in saving life of people. And then you have to compare 2 measures that are not comparable, because you cannot compare economic benefit with life of people. And then there are plenty of methods in the literature which are called multi-objective optimization or multi-objective robust decision making. But let's focus on a single performance measure. So we have to agree it. And then we need to understand the candidate strategies. And this is another important decision, grassroots decision, because do we want to consider Adam? And people would say no, because I don't want Adam above my head. And can we consider reinforcing the levies? And people may say no, because I mean, raising the levies, a person that understands how things go also realizes that you may increase the risk because you increase exposure. You may imply increase of exposure. So, is it a strategy to do anything? To do nothing? Don't do anything? And people would say no. Of course, this is the question that every day we. This is the problem that every day we say, we emphasize, and we need to do something. Okay, but the strategies, and I anticipate this is a key issue, because usually when you have an effective strategy, you always find some people against it. And at the end of the story, I mean, you need some brave decisions, some unpopular decision to be taken. And I mean, this is also a duty of the politics, that sometimes they should indeed take unpopular decisions, which I understand in a democratic system it's a problem. Okay, it's really a problem. Okay, so we identify the strategies, and then in the next step, we evaluate the system performances. So for each strategy, we apply our performance measure, and then we compare alternatives. And then at the step 3, we assess the vulnerability. We take the climate scenarios, and then we assess the vulnerabilities. So we identify the scenarios with respect to which the strategies may fail. And then after you discovered the scenarios that are weak, that are vulnerable, then you can refine the strategy. And it's an opportunity to see, okay, can I correct the strategy? Like the dam is vulnerable to 2 scenario over 10, okay. And if we make a dam of reduced size, what happens? Or increased size, what happens? And so you can adjust the strategies, and then finally you converge to your adaptation options, and then you take a final decision, but in the final decision, this method, robust decision making, at this stage introduces the information regarding probability. So when you have the final picture, you may tell stakeholders, look, this scenario is really unlikely. And this may be an opportunity for involving risk management. Maybe an opportunity for taking a more risky approach in order to benefit from potential opportunities. But of course, if you want to understand if the risk is tolerable, as we know, because we studied the risk-based adaptation design, we studied the risk equation, we need to improve some information regarding probability. Okay, so robust decision making indeed says, okay, let's take into account probability at the very final stage. Okay. And of course, there are several applications of this method which introduce specific performance measures, specific case studies, specific estimates for probability. And this is indeed an interesting option because it's robust, but at the end of the story, there is a consideration also of the risk, and there is the inclusion of willingness to take some risk. Okay. Questions? This is a narrative, as I said. I just would like that you understand the concept. Okay. I hope you understand that it's a bottom-up and it's robust because it looks at several scenarios and identifies, takes into consideration also the possible worst outcomes. Okay. Still, what could be a limitation of this method? A limitation of this method may be that it's true that there is risk management at the end, but this method doesn't consider in an explicit way the opportunities, because it doesn't consider the fact that uncertainty may be an opportunity. And let me give you a very trivial example. So there are some climate models that predict for the future terrible situation, or let's say an increase in a more scientific way, in a more scientific wording, an increase of the risk. And of course, this is concerning, but the prediction is uncertain. And, if the uncertainty is very low, you may say, okay, in any case, even considering uncertainty, the risk is increasing. But if uncertainty becomes larger, it may include the option no change, so no increase of the risk. So you understand that in this case, a large uncertainty may be associated to an opportunity, because if in the future there is no risk, no additional risk, I can use my resources in a more convenient way. So uncertainty may also be an opportunity. But also, if you think of everyday life, uncertainty implies that when there is uncertainty in an evaluation process, for instance, sometimes I tell my students who apply for very competitive research grants, you know, it's unlikely that you get it, but there is uncertainty. It's unlikely. Why? Because, you know, you are in a situation that you compete with people from the north of Europe, native speakers who are more advantaged. On the other hand, there is uncertainty. And my conclusion is, if you don't buy the ticket, you don't win the lottery. So buy the ticket. And uncertainty may lead you to win. And indeed, it happened to me several times. Sometimes I competed in some research grants where I had a very low probability, but there was uncertainty. And thanks to uncertainty, I could get them. And this happens not frequently, I mean, but sometimes uncertainty brings unexpected windfall. What is a windfall? A windfall is, in Italian, we call it manna dal cielo. It means something, a benefit that is unexpected, and a benefit that is surprising, that you are not really expecting, but it comes. And this is due, this windfall, sometimes, if it is unexpected, it means that it's due to uncertainty, because you make your best prediction, and your best prediction is no benefit. But then the presence of uncertainty, when something comes unexpected, you understand, it's due to uncertainty. The presence of uncertainty may bring some unexpected opportunities. So robust decision making is not taking into account the fact that uncertainty may be an opportunity. And therefore, about 20 years ago, this the decision method, the robust decision method, was introduced, called InfoGap. Why InfoGap? Because InfoGap works on uncertainty, and uncertainty due to lack of information. And this method was proposed 20 years ago, and in the framework of actually water resources management. Water resources management has been a field very relevant to decision theory, because management of reservoirs, management of water resources, it's really dominated by uncertainty, and there were a lot of work in water resources management on decision support systems. So this model is, in principle, it is very simple. The concept is simple, this method. On the other hand, given that I want to give some details and give you an example, there is some analytics that is introduced and the symbology, which makes it not really easy to understand it at the first glance. So my suggestion for you, I think in the web page there is everything you need for understanding it. Try to focus during the lecture on the concept and also the questions, but try to focus on the concept. The concept is very simple. And first, the concept is the recognition that uncertainty may be an opportunity, and therefore to look not only at the worst outcome, because in the presence of uncertainty, min-max looks at the worst outcome and select the best worst. Here, the method also looks at the outcomes that may be larger than the expectation. So looks at also the max outcome in the presence of uncertainty. So you have two scenarios. You don't look only at the minimum and at the number 2, but you look also at the number 5. Okay. So, and the concept is, let me look at the maximum level of uncertainty that I can tolerate while keeping the system performances acceptable. So it starts from the same premises as robust optimization. Again, it doesn't look to uncertainty estimation at the beginning. Perhaps it reverses the strategy. It looks at the max uncertainty that I can tolerate for the future climate in order to keep acceptable performance of the system. On the one end, I say again, it looks at the max level of uncertainty that gives you still an acceptable performance of the system. On the other hand, and this is the innovation of this method, it looks at the minimum of uncertainty that can lead to an unexpected windfall. So it looks at uncertainty ranges. On the one hand, the max level of uncertainty to keep the system acceptable. On the other hand, the minimum level of uncertainty for allowing me to get an unexpected luckiness windfall. And you understand the difference with the difference between looking at the max, looking at the mean. I say again, when I look at the worst outcome, I want to get an estimate of the max uncertainty that keeps the level of the system, the performance of the system acceptable. And why I look at the max? Because the larger, the better. So if I see a system that in order to perform in an acceptable way allows me only a tiny range of uncertainty, I'm not happy. Because it means that the system under uncertainty may fail very quickly. If I look at a solution, at a system, which even in the presence of a large uncertainty is acceptable, I am happy. Because, okay, the system is okay even with a large uncertainty. The larger, the better. When I look at the unexpected windfall, and I ask myself, what is the level of uncertainty that allows me? My best prediction is that I'm not getting a windfall. I'm not getting a luckiness. But what is the level of uncertainty that may lead to me to get a lucky future? And if somebody tells me very huge uncertainty, I mean, you need really that everything is wrong to bring you a lot of money, so you are not happy. But if somebody says, my prediction is that you don't get a lot of money, but even a small change in my prediction may bring you really a treasure, you are happy with the small uncertainty. So the smaller, the better. And this is the concept of InfoGap. So it looks at the whole system. So if I had to describe in a narrative way, I would close here. It looks at the whole system and looks for unexpected windfall and worst outcome, and uncertainty ranges that keep the system acceptable, and uncertainty range that gives to me unexpected windfall. The larger, the better for uncertainty for the minimum performances, and the smaller, the better for uncertainty for the unexpected windfall. This is a narrative description. And then we can make an example. Questions before I move forward? I mean, I think this is really interesting because this is already discussed, okay? And I think it is really interesting because it's really looking at our problem in a comprehensive way, okay? And I think, yeah, same thing, already discussed. I can move forward because this is the narrative introduction. And this is not discussed. So what are the three essential components of the method we are talking about, of InfoGap? The model is the performance model. It's not the model giving the future prediction, the future climate scenarios. It's not the climate model. The model is our performance measure, in which way we evaluate the effectiveness of a strategy, of a solution. And it is typically a mathematical relationship that gives a performance measure. Okay, this is the model. And then we need to set the performance requirements. So what is the minimum performance that we want from the system, and what is the performance that corresponds to the windfall? So basically, we can say, I will make an example of water resources management with the next slide. And then I need an uncertainty model. An uncertainty model because at the end of the story, in a way, we need to quantify, to identify what is the max uncertainty corresponding to the minimum requirements, what is the mean uncertainty corresponding to unexpected windfall. So I need also an uncertainty model. Okay. I think, yeah. So I anticipate that we need to define two functions that allow me to understand the trade-off between robustness and opportuneness of the system. So the trade-off between the max uncertainty that I can tolerate for keeping the system performances at an acceptable level and the mean uncertainty that is needed to get the unexpected windfall. And so I will need to define two functions in order to evaluate the robustness of the system and the opportuneness of the system. And by comparing these two functions, I can get an indications for my decision. At the end of the story, you need to take a decision, and the decision is a trade-off between robustness and opportuneness. And the best thing is to develop two functions. Why? Because when you present results to people, you need to be very clear in what you did. And this is why also in your respect, I introduced the concept with a narrative. And in order to be clear, if you present graphs, it's much better. So instead of presenting equations, if you present pictures, it's much better. I think now the example is introduced. So I prefer to introduce an example so you can better understand how the model works. Okay, so let's refer to a case of water resources management, and let's denote with the symbol X the future prediction affected by uncertainty of water volumes, for instance, in millions of cubic meters, that is annually managed by an irrigation board. So the irrigation board needs to derive a prediction for the future of water resources availability. And this prediction is denoted here with the symbol X. So we know an estimate value of water flow. So we have a model that is not the performance model, is a prediction model, which is available to give future climate and future best prediction of water resources availability. Hopefully, we have also an estimated error, and but it's not really a probabilistic error. Let's say that we need here to introduce an estimate of uncertainty. Let's call it S, okay? And again, it's not associated to a probability. Let's take the worst case, okay? And we can say that our prediction is X plus minus S, but S may be also exceeded because given that it's not a precise estimation of error, it's an indication, okay? Like 100 millions of cubic meters of water plus minus 10%, okay, more or less, let's say, you know? So it's a quantitative estimation of uncertainty. Okay, and let's assume that our performance measure is given here on the screen, is given by this very simple function, okay, with parameters that let's suppose are estimated. I'm not giving the parameter values. I just want to show you here what is this function. So if you put the water volume, the prediction on the horizontal axis, and for some values of the parameters, you get a benefit in, for instance, in millions of euros that is asymptotically converging to a max. And this is quite typical in water resources management. If you have zero volume available, you get zero water, you get zero benefit. And then the benefit increases, but tends to an asymptotical value. So the concavity of the curve is headed towards the bottom of the graph. Why? Because when you reach an optimal allocation of water, if you exceed it, you don't get any additional benefit. So this is quite typical. So you get something that may behave like this. And of course, we may visualize on this graph the best estimate. It's not visualized here. The best estimate of x, we will call it in the following x tilde, okay, x with the tilde above the x. And to the best estimate, you get, in correspondence of the best estimate, you get a benefit, b tilde. And it's not visualized here, but of course, this is a picture of the performance model. If you plug into the picture the best prediction, you can get here the best prediction, and typically it will lie something that is typically is not close to the asymptotic value. Typically, you get something in between. Okay. Okay. So now the question is. The prediction is uncertain. So let's define an uncertainty model. And a very simple way of defining the uncertainty model may be by taking the relative error. So, I mean, if you take the future, the best estimate is x tilde, as I said, but the future will be not necessarily x tilde. The future, let's call it x simply. And so let's compute the difference between the real future x and the best estimate. And let's divide it by the s. S is our guess of uncertainty, okay? Absolute value, because we don't care for now, and we want to define a range of uncertainty. So let's say that this range of uncertainty should be lower or equal than a given value h. So what is h? Is a relative error. We fix a max of the relative error. Relative to what? Relative to our previous estimate of uncertainty S. So this is how in InfoGap uncertainty is quantified. You may devise a different way. So don't look for here for a logic other than trying to be in a way very clear, very transparent. And you may say it's not very transparent because I really don't understand why they need a preliminary estimate S however, if you think of a specific situation where you have a best prediction and you have an estimate also of uncertainty, which is not quantitative, and I think it is quite logic that you want that this H is this division of the actual error, this ratio between the actual error, because at the numerator here you see the error that is the real one, and divided by my error expectation is as low as possible. And therefore, ideally, you want that H is at most 1, but H may be larger than 1 because our estimate of uncertainty is not precise. So it's a way to express in relative terms what really happens with respect to what I am expecting. Okay. Okay, now, how can we express our wish that once I fixed a minimum level of benefit, B critical, BC here. So let me fix a minimum level of benefit. I have an estimate B tilde of, which is my best estimate. I'm not sure of getting it. Let me say, okay, I can tolerate a benefit that is lower than B tilde, a benefit B critical, BC that is lower than B tilde. Let me define it. What is the critical benefit? To keep the system functioning, okay? And let me estimate what is the level of uncertainty that keeps the system functioning. So what is the level of uncertainty that gives a benefit that is at least B critical? So let me go back to the previous figure, and let me try to reproduce it on the blackboard. Okay, let me reproduce the figure that you see on the screen over the blackboard, and let me visualize there the best estimate of benefit and the critical one. Okay. Okay, this is my figure. This is my W. This is, let me call it W. No, X, sorry. And here I have the benefit is B. B. And what I see on the screen is something, let me, I'm not displaying numbers, but it is something like this. The numbers are on the screen, okay? And here I can identify a B tilde, X tilde. This is my best estimate. And here I get B tilde. Let me change a little bit. Okay, let me keep it. That's fine. I wanted to change it because the situation is too good. If I have a decision-making problem, probably my best estimate is giving a lower benefit. Here I'm close to the max. It's not really a big problem, okay? But anyway, let's keep it. Now, this is the benefit that I am expecting, my best estimate. If I get it, I am okay. And let me define now a lower value, X critical, that is associated to the mean benefit, B critical, which gives still acceptable performance of the system. So I define B critical, and my question is, what is the max level of uncertainty here, or the max level of uncertainty here that I can tolerate in order to make sure that I still have a satisfactory performance. And this is the difference X minus X tilde, which is reported in the next slide, which is divided by S, which is my preliminary estimate of uncertainty. Okay, so I fix X critical is getting into this relationship. And then let me fit a benefit corresponding to the unexpected windfall. Okay, and let me call it BW. And BW here is a bit of a problem because let me, okay, make it like this. It's associated to XW. And this is the uncertainty. It's related to the uncertainty, the level of uncertainty with respect to the best prediction that leads me to the unexpected windfall. Okay. And then these levels of uncertainty are characterized in InfoGap by dividing them by the preliminary estimate of uncertainty S. And this brings to the next equation, where here you see a generic X. It can be, you can plug in into this equation X critical or XW. It's a generic X. Now, let's then define the robustness function. And the robustness function looks for the larger uncertainty. The larger, the better. So you see here, the robustness function depends on the critical value of the benefit, of course, because you see that it's the critical value of the benefit that identifies the uncertainty that I need. So the robustness function depends on the critical value of the benefit, looks at the maximum, because I'm looking at the larger uncertainty, the maximum of H with B that is larger than B critical. So I impose that B is larger than B critical, and I'm looking for all the possible values of X within the uncertainty range, and I look for the minimum, and this minimum still larger than B critical, and I look for the max value of H. So the larger uncertainty quantified through this ratio. So as I said, as I anticipated, the math requires a little bit of elaboration, but the concept, the concept is precisely what I introduced to you before. So critical value of the benefit, I look at the uncertainty, which is the max, the larger uncertainty that gives to me a benefit that is larger than the critical one. And then, of course, the symbology may require a little bit of elaboration. But this is the definition of a function. It's a function of the benefit. It's a robustness function because it gives to me an indication, depending on B critical, of the level of uncertainty, the max level of uncertainty that I can tolerate. Yeah. What is S? S is a preliminary estimate of uncertainty, a very qualitative one, which is introduced in the method because the method presupposes that you have an indication of uncertainty. And therefore, the method wants to take it into account. You may avoid it, actually. You may elaborate this equation by removing S and just looking at the difference between the reality and the best estimate, and work here with just with the difference. The method decided that people who proposed the method decided to take into account a preliminary estimate because basically they believe that this H has this meaning. If H is lower than 1, you get an uncertainty that is lower than your initial guess. If H is larger than 1, it means that your estimate of uncertainty was too optimistic. So they thought that in this way it's clearer. But indeed, I think that the mathematical development is unnecessarily elaborated. Unnecessarily, because the concept is clear. I mean, I look at the minimum performances here, and my question is, what is the max level of uncertainty in terms of difference between the reality and my best prediction? And in relative terms, for the decision, what is the max level of the difference that I can tolerate? So what is the max level of uncertainty? And this is what we call the robustness function. And you can easily identify the function with an experiment in this way. In our case, I did an elaboration of this. I go back a couple of slides. An elaboration of this performance function with some assigned value of the parameters, and it can be easily demonstrated that, I mean, in terms of the critical benefit, if the critical benefit increases, the level of uncertainty goes down for sure. And here on the vertical axis, you see the level of uncertainty. And in this, one means that your level of uncertainty is precisely identical to the preliminary expectation. And this is why they wanted to introduce this dimensionless quantification. One means the level of uncertainty corresponds to what I am expecting. And of course, lower than 1 means lower uncertainty. And if it is higher than 1, larger uncertainty with respect to my preliminary expectation. But the moral of the story here is that if you reduce uncertainty, the critical benefit is increasing. Or I can say it the other way around, which is probably more understandable. If you lower down the value of the critical benefit, if you reduce your critical expectation, you can tolerate a larger uncertainty. Okay, and this is the function. This function possesses a property which is called zeroing. What does it mean, zeroing? It means that for zero uncertainty, what does this mean? It means that the model, the best prediction is what you get. So for zero uncertainty, the critical benefit should correspond to the benefit that you get with your best prediction. This is called the zeroing properties. Zero uncertainty means that you get your best estimate, and it means that then if you bring your critical benefit to the benefit corresponding to the best estimate, it means that you don't tolerate any uncertainty. If you go down with the critical benefit, then you get to larger tolerated uncertainty. Okay. So what is the usefulness of this function? It is very useful because it allows to you to make an evaluation of robustness. So if the irrigation board gets a benefit, estimated benefit of 24 millions of euros, okay, 24, then they can fix a critical benefit like until 20 millions, I am fine. Okay, 20 millions, it's here. It means that you can tolerate an uncertainty that is lower than what I am expecting, is 0.6. So, you know, it's not very robust. Or let's say if they say, fine, with 10 millions, I am okay. Of course, I'm not happy, but I can still survive. Okay, 10 millions. I go down 1.4. 1.4 means 1.5 the uncertainty that I am expecting. So I'm quite fine. It is a useful indication that you get from here. And you can get the same indication with robust decision making up to now. Okay, robust decision making, the previous method, is basically, if you apply it, it can be applied in this way. And you stop there. You stop there. In robust decision making, then you should evaluate all the scenarios and say, okay, so if I have a scenario giving me 5, then I'm not happy. But if I have also a scenario with that can give me 20, it may compensate for the other scenario. And then I look at the probabilities. But robust decision making can be applied in this same precise way up to here. Because InfoGap now looks only at robustness. And this is a nice example of a robustness function. Okay, now we have to look at the opportunity. So we have to look at the opportuneness function. Let me go back one slide. You understand that in this way, we define the robustness function. And in the same way, we can define the opportuneness function. Of course, we have to use BW instead of B critical. BW here. And then we don't have to look at the max of uncertainty. We said that we are interested in the minimum of uncertainty. So what we need to introduce to the opportuneness function is an expression that is like dual with respect to this one. Okay, I plug in BW here, I put the minimum here, and then probably I have to put a max here. Okay, and this is our expectation. So let's see how we can write it. Let me see this slide. I think, yeah, the slide is already commented by me. So, I mean, look at the last bullet point. So the question asked by the windfaller is, what is the lowest horizon of uncertainty to make a windfall possible? Not necessarily, of course, given for sure. It's possible. Okay, so we need to fix BW. Okay, and of course, let me see, BW with, let me see if there is, this is correct. I don't think it is correct here. Let me check on the web page. Sorry, 1 second, because BW is larger than B tilde usually. BW is larger than B critical, of course, but should be also larger than B tilde. Let me check on the web page if it is correct. So this is BW. BWs. Yeah, you see here it's correct in the web page. We need to fix a BW with BW larger than B tilde. B tilde is corresponding to the best estimate, larger than B critical. So let me make a change here. See if it is easy. Let me see if it is easy. Okay. And let me check. It's not easy. Okay, so I hope you understood that BW is larger than B tilde and B tilde is larger than B critical. Okay, so and in the web pages it's correct. I will correct also. I will make the change also here, but it's not quick. So we define BW, which is larger than B critical and larger than B tilde, which is the best estimate. And the question is, what is the lowest horizon of uncertainty at which windfall is possible? And this is the equation. So minimum of H with max of B larger than or equal than BW. And I go back a couple of slides to remind you what is the definition of the robustness function, and you will see that it's dual of this, okay? Let me go back. You see, BW instead of BC, there is a min in front of the curly bracket, and a max between the round parentheses, okay? Look at this figure, and then, or let's see, this figure, we can put it here, okay, and then this one. So you see the difference? Max in front of the curly bracket, min between the round parentheses, min in front of the curly bracket, max within the round parentheses. And then I plug in BW, and this is the opportuneness function. And of course, the opportuneness function starts from the best estimate 24, which corresponds to zero uncertainty. So it is another zeroing properties. You have zero opportunity if you have zero uncertainty. Zero uncertainty, you get the best estimate and zero opportunity. But if you allow some uncertainty, then the opportunity goes up. Let's make the break now. Do you have any questions? And during the break, let's reflect a little bit on this figure. Any question? Good, thank you. Okay. Okay, so first of all, questions? Okay, and there could be kind of relevant question by you, like, is this, what should we expect in terms of questions at the exam related to what we discussed today? First, today we close with the topics for the exam first call. So more clear. We close the lecture next Monday, but what I'm discussing next Monday will not be asked at the first call of the exam. Okay, the second call, yes. Okay, is it clear? Yeah, perfect. But what I'm teaching today, yes, it is also a possible subject for the first call. So once again, it's not a big issue if you don't remember the equation that you see on the screen now, and just try to focus on the concept. So a possible question in the quiz or the oral may be, what is the concept underlying the info gap decision method? So if it is asked at the oral, it means that it is quite a general question and you have to be prepared to speak for a few minutes, like a couple of minutes, explaining the concept for the info gap, or what is the concept for the robust optimization. And if it is a question at the oral, again, you have to be prepared to speak a couple of minutes or even less. I mean, no problem. In the quiz, you may find a more specific question like, what is the distinguishing feature of the info gap robust decision method? And you may find three alternatives. The first one, like it considers also the opportunity that may be delivered by uncertainty, which is the correct one, and the other two options are plain wrong, clearly. So it may be something that is related to your knowledge of the concept, okay, of the info gap. In the quiz, it's absolutely not necessary. It's absolutely unlikely that you will be presented with an equation and you have to write the equation. This is impossible. You may be presented with an equation in three solutions, two plain wrong and another one correct. Like in this case, you may be presented with this equation and two versions that are plain wrong. And but plain, when I say plain, it means really plain wrong, and you have to recognize the correct one. So this may happen, but it is more likely in the quiz that you are asked to select the right concept underlying a given technique. And in the oral, of course, if you are asked a question on the info gap and you write down the equation during the oral that you see on the screen, it's not needed, but of course it's a distinguishing feature if you can write the equation. This in any case, okay? So you are not required to learn by memory some relationship like this one. It's not strictly required that you learn it by memory, but if you are able to write it down, it is a distinguishing feature, and then it's up to you. My suggestion is, if there is something that really is interesting to you, looks interesting to you, then it may deserve to look into the details, because you know, if you are passionate about a certain topic, it's likely that this motivation comes out even during a short oral. So my suggestion is, if you don't have to learn everything by all the details, but if there is something that looks particularly interesting to you, it may be worth the effort if you want to get a distinction. Is it clear? Okay, good. So when you look at this graph, of course, you will have this graph for a couple of alternatives or 3 alternatives, and you clearly understand that it gives to you a clear picture of what is the best estimate that you get if you had no uncertainty, and what is the drawback and the opportunities that are related to uncertainty. So basing on this graph, you discuss with the stakeholders, and maybe that you put 3 of them on the same page. Like if I build a dam, this is the robustness function and the opportuneness function. If I raise a levee, this is a robustness function and the opportuneness function. And you put them on the screen, and then you discuss with the stakeholders what is the best option, and basing on some objective information, and basing on a transparent approach. Of course, the decision may still be not easy, so there are further forward in decision theory additional methods that allow you to deal with this step of the decision making. So once that you have all the information, still this method is not delivering to you the best solution in the presence of uncertainty. If you have no uncertainty, of course, it's clear. A best prediction, the benefit, and that's it. And you have another alternative, okay, best prediction, the benefit, and it is quite easy to make the selection because you take the best benefit and the option with the best benefit. But when you have uncertainty, of course, this step of the decision is still not easy. And there are other methods that are conceived to deal with this step. And maybe that we have the time next Monday to discuss some of them. And it is indeed part of this lecture to move a step forward. Okay, these considerations that I am now drawing are those that you can see on this lecture, and I think now we can move forward with the next one, the last robust decision making method that I would like to discuss with you, and through a narrative, not really going into the details. Okay, and these are considerations that I already made, so we can go through it. Maybe one thing that I didn't say, which is a reflection that comes to my mind now that I see these sentences, and I go back here. The slope of these curves, of course, it's very relevant, and these are, for instance, here the slope of the opportuneness function. You see that it is indeed it is attractive in this picture. It is we are tempted to benefit, to seek for some windfall, because when it is so steep, it means, it is the opposite, the other way around. When it is so steep, you see that you can't gain really a large windfall. You need a lot of uncertainty for gaining even a small windfall, a small increase of benefit. So when it is so steep, it's not very attractive. And you are more tempted to go with robustness because you see that even with a small decrease of benefit, you get quite a significant increase of uncertainty allowed. So in this situation, you are not very tempted. In some cases, you may have an opportuneness function that goes quickly up in terms of benefit, even with a small uncertainty. And in this case, you may be more tempted. So the slope of these curves is relevant in evaluating the best decision. Okay. So next one, decision scaling. It's again a bottom-up analysis approach. And I think that, first of all, why it is called decision scaling. It has been conceived that this method has been proposed 10 years ago. 10 years ago, again in 2013, so 11 years ago, again in the context of water resources management and in the context of decision-making under climate change. And why decision scaling? Because see the second bullet point, and it investigates the appropriate downscaling of climate information that is needed to best inform the decision at hand. Because climate information is given at different scales, and the finer the scale, both spatial and temporal scale, the finer the scale and the larger the amount of data that you have to manage. So going at very fine spatial and temporal scales requires a lot of information, additional information, and involves additional uncertainty, because it's clear that if you want to predict the future rainfall over the Emilia-Romagna region, you have an uncertainty that is smaller than predicting the future rainfall in Bologna. If you go to a very specific spatial resolution, and if you go to a very specific date into the future, so prediction of rainfall in 2050 in Bologna, you understand there is a lot of uncertainty. And therefore, the decision on the level of downscaling, so going to finer and finer and finer scales, entails a decision on the level of uncertainty that you can tolerate. And therefore, this is why they called it decision scaling, because it was an aid to identify the best also resolution in terms of spatial and temporal scale for the data. And so basically, let me refer to this graph here, okay? Once again, top-down, robust decision-making, remember, candidate strategies. So robust decision-making starts from strategies, so solutions. And then solutions are evaluated against scenarios to identify vulnerability. And then it may be a circular approach. So vulnerability, refine vulnerability with new strategies, again, evaluate strategies against scenarios. Now, decision scaling starts from assessing vulnerabilities. So current problems, typically it is used after a flood. Like, okay, a flood occurred and clearly showed that we are vulnerable to this, this, and this, okay? And then these vulnerabilities in a future climate, how will develop? Will we become more vulnerable, or in the future there will be an improvement of the situation? Like, for instance, for droughts, it's not clear what the future will reserve for us. Maybe if you look at our history in Italy since 1950, we didn't have any huge drought. So maybe that the future is okay, let's look at the future scenarios and see what happens. And this is what we are actually doing for droughts, okay? And then the method allows for further information, because the method recognizes that it's not only the future climate scenarios that you have to look at, but it may be that you have, for instance, demographic development that gives to you other indications that are useful, because exposure also depends on the societal development. So let's suppose that, okay, you have climate scenarios that for this region don't predict a good future, but you have a prediction of socioeconomic development that shows that exposure may decrease. So this is to estimate risk. Here it is used the term vulnerabilities, so it refers only to vulnerabilities actually. But in terms also of risk, you may get some information related to exposure. Or vulnerability, you know, that depends on the protection. So is our protections are going to increase or decrease in the future? So the method allows for further information. And then basing on the vulnerabilities and basing also on, here it's not explicitly mentioned, but you can also consider exposure, then defines the strategies to minimize the risk to systems. And this is the workflow that you see. It's a bit different from robust decision making, but the concept is very similar. Okay, the difference is that here you focus on you start from vulnerabilities rather than strategies. The strategies are identified at the end, and here there is the explicit allowance for further information, but the concept is very similar. I just wanted to give you another example because I think it is instructive to see that they overlap to some extent. To some extent, they use the same information. And you may also devise some intersections, some mixing, depending on the context that you are working on. So depending on the information that you have, depending on also on your audience, because the humor of the audience is extremely important also in the selection of the best approach. Okay, and the humor and also the willingness to pay of the audience, for instance, it's extremely important. This is willingness to pay is another hot topic in the literature. So estimating willingness to pay of the citizens, for instance, in climate change mitigation, reducing of CO2 emissions, willingness to pay is extremely important because it is a social cost. So carbon tax, whatever, and if people are against this, there is no way for the political parties to I mean, there is no way. There is the way, but the way is to take a very unpopular decision, and it is not always easy in a democratic system to take an unpopular decision. Okay, and let me just see. I go to the web page because this is not reported in the slides. There is a small section on the comparison between robust decision making and InfoGap. And this section, I think it is interesting because it shows to you that indeed there are contributions in the literature that compare them. So there are, sorry, this is the wrong, yeah. And there are contributions that are cited here where people tried in the context of climate change impact assessment and the climate change solutions identification. There were people trying to compare methods, and in some of the studies they came to the same conclusion, and in other studies they found slight differences. Actually, you know, it is quite obvious and understandable that there are differences in the final outcome. If you have to evaluate two alternatives to a problem, to a climate change problem, it's clear that basing on the use of a different information, you may reach a slightly different conclusion. And it depends also on the differences between the two alternatives. If the alternatives are radically different, you know, you may expect that the conclusions are the same, but sometimes you have several alternatives and the differences between them are very small. So you may expect that different methods lead to different decisions. And you may also expect that a different audience with a different willingness to pay comes to a different conclusion. And also in countries with different public debt, of course, richer countries have more options and are more willing to pay in order to get protected. So it is, when we consider the environmental risks in Italy, sometimes we blame the fact that our parties, our political parties, don't take decisions, but the public debt is indeed something that is really relevant in taking decisions that involve a large use of public money, of public resources. And this is something that very often people don't really understand. When we talk about public debt of a country, people in general push for increasing it because they don't see a relevant effect on their pocket, an immediate effect on their pocket. So the fact that the government, the state, has a huge debt has not a direct impact on our pocket. Instead, if they reduce the pensions to compensate the debt, of course, we see an effect on our pocket. So we indeed rely on the public opinion in order to take decisions, but the public opinion very often doesn't see the consequences that the public debt, in particular, has on themselves. They don't see them because it is indeed difficult to see them. But this is a case where the public debt means that the population is more exposed to environmental risk, is more exposed to climate change, and maybe that people don't care about climate change because they don't really see climate change as a risk. But when you talk about droughts, when you talk about floods, so one of the reasons why Italy is not well protected against floods is the public debt, indeed. And when people push for increasing the deficit of the government, they don't realize that in this way they are getting exposed to sanitary risk, to environmental risk, because it's clear if the state doesn't have enough money to invest on the health system, on the public health system, to invest on the public works for getting protected against earthquakes, against the floods, against droughts, then the disaster happens, and you understand why decision making is important. Same thing for fiscal evasion. So people clearly don't understand what is the indirect effect of fiscal evasion. They see the effect on their pocket, which is a benefit, because if I evade taxes, it's a benefit for my pocket, an immediate benefit. But then there is an indirect effect, which may be really, really dramatic, because fiscal evasion means larger public debt, means et cetera, et cetera, et cetera. Okay, this is a kind of reflection that it's in a way to motivate why we focus on decision making. Okay, just a brief mention to multi-criteria decision analysis. I already made it. So basically, I already mentioned that the performance measures can be more than one, and there is a large literature focusing on seeking the best compromise, not only between different solutions, but also between different objectives. So I evaluate several possible solutions with respect to several performance measures of the solution. There is a large literature, and there are several ready-to-use software for applying these multi-criteria decision analysis in general. Don't forget that sometimes we assume that these methods are complicated, are to some extent complicated, like also robust decision making, to understand. But once that, and it's necessary that you understand them, because you don't have to apply, as I said several times, a method without understanding what it does. So it is important that you understand it. On the other hand, the ones that you understood the concept, you have several softwares available that can drive you. And today you can also use ChatGPT, like can you suggest our program for multi-criteria decision analysis? And you get a lot of information ready to be used. But once again, make an effort to understand what it does. Don't rely on, especially if you rely on ChatGPT blindly, on what ChatGPT suggests. But we are not looking into details for this. Okay, now, let me see. I have 15 minutes, and this actually would be the last topic that I want to discuss with you. And let me just say, this is not for the first call of the exam, okay? Good, the second call maybe. Before I move forward, do you have any question? Okay, good. So I mentioned to you that even with this information available, sometimes at the end of the story, it becomes difficult to make the final step. So we may use robust decision making, and I said in robust decision making you get to a point where alternative strategies are to be compared with the scenario and to be validated, verified against the climatic scenarios. And I said you may use this validation to refine the alternatives, and at the end of the story, you may also use probabilities, I said, in robust decision making to manage risk and select the best one. But I didn't say anything on how risk is to be managed. In InfoGap, I'm sorry, you know, during the weekend, I'm still going to ski, but you know, it becomes more complicated. You need to go very high altitude, and the climatic conditions are not always the best. So once again, and in InfoGap, I said, okay, you can use opportuneness function and robustness function, and in this way you can select the best alternative. But I didn't say how to make the last step. So these methods are very useful because they give to the audience the information that they need, but still it may be difficult to manage a decision. And therefore, there is a last step that has been made in the literature to aid, to support this final step. And this technique that I am suggesting is very popular, has been introduced 50 years ago. It's indeed a little bit more than 50. And it is indeed very popular, has been used in several technical problems I was involved. So I said, this is a useful information for the students. And I think it is indeed providing an objective way for managing an audience, provided that you gave all the information to them, okay? So what is the concept here? The concept is, first, to decompose a complicated decision into smaller and simpler sub-decisions. So I have a complex decision to be taken. I try to structure them through a sequence of steps, and each step involving a simpler decision. I make an example. Let's suppose that you have to evaluate 3 alternatives, like, for instance, a dam, a levee, or a nature-based solution. If you compare the 3 of them, it's difficult to say for the people what they prefer. It's much better to split the decision in pairs of comparison, like, would you prefer the dam or the levee? Or would you prefer the dam or a nature-based solution? Would you prefer a nature-based solution or a levee? It's easier. So if we could find a way to decompose a complicated solution into a sequence a complicated decision into a sequence of simpler decisions, it would be easier. So this is the underlying concept. So you see here, once the hierarchy is structured, the decision makers evaluates its alternatives by comparing them to each other two at a time, by using pairwise comparison. This can also be used to evaluate performance measure. Should I use economic benefit or loss of lives or environmental impact, minimization of environmental impact? And if I have three criteria, what criteria should I use? Or in the case of criteria, I want to mix them through a weighted combination. What is the weight that I should give to the economic benefit with respect to the life of people, with respect to environmental impact? And if you compare them 2 by 2, it's easier. It's easier to make the selection. So this comparison may be applied both at the criteria that you use, but also at the solutions that you want to identify. By the way, this method became so popular that you find a Wikipedia page, which is linked in my website, which is well done. I think it is clear. It is clear. So what is, once again, the purpose? So this is the concept. Destructuring a complicated decision into simpler decisions, a sequence of simpler decisions. This is the concept. What is the purpose? To convert preferences to numerical values. So we need a quantitative assessment. Preference is, it's not quantitative by definition. This is the objective. And there is one more thing that I wanted to say, which I don't remember now, but anyway, I will remember it later. So let's see how the method works. And let me give another example, because I think it's much better if we explain it through an example, okay? Again, let me refer to a water resources management problem, but you can refer to whatever problem we consider. And let's suppose that we have 4 criteria that we want to use. So it's not only one benefit. So the 4 criteria are net benefit, environmental impact, the impact on the river flow regime, and CO2 emissions. Okay. Let me better explain. Net benefit is the economic benefit that you get from a solution to a water resources management problem. I still don't list the solutions here, the candidate solution. I'm just discussing for now the criteria. So economic benefit is one criteria. Environmental impact, it's another criteria. So I want a solution minimizing the environmental impact. Impact on the river flow regime, because when you take water from a river, whatever method you use, you have an impact, you generate an impact on the river flow regime, because there is less water in the river. So the fishes, the ecosystems, and the tourism, the society in general suffer from it. So we want to minimize this impact. And any solution involves CO2 emissions, and we want to minimize the CO2 emissions. So what is the reason why I discussed the criteria before the possible solutions? And this is the thing that I was forgetting to say earlier. So when possible, this is a general principle, suggestion, rule of thumb for decision making. When possible, try to discuss first the criteria and then the solutions. Because once that people know the possible solutions, the alternatives, they change their idea on the criteria. Because, of course, if you know that a dam is above your head, then you may think, okay, I don't want it, absolutely. So what is the criteria that may suggest the dam? Let me downgrade this criteria. Okay, so for instance, I can understand that probably the dam gives a larger net benefit. So let me downplay the net benefit. Let me give a lower preference to net benefit because I don't want the dam. So it is quite typical. And while if you start from the criteria, it's more objective. Let me give you another example. Let's suppose that you have to make a selection for a position for a job. You don't know the candidates. Okay, it is usual practice and prescribed by the government that public selection for public jobs, commissions have to define the criteria before knowing the candidates. Why? It's clear. Because if I am a member of a commission and I knew that there is one of my students as a candidate, I know the strengths of my students and I may give more weight to the criteria that give more recognition to the skill of the people I know, of my students. So if I don't know the candidates, then my choice is more objective. And of course, this is something that you not always can apply because, you know, sometimes we know the candidates because, you know, maybe that we know in a way the possible audience of a call for a job. So we may get some guess of the candidates, but still we don't know the CV, we don't know the details. So it's much better if you focus first on the criteria. It is unbiased, it's more objective, and it's ethically more correct, which is an important thing. Remember, ethics, maybe I never spoke about ethics of your job. It's very important when you take a job. It's very important that you study the ethical code of the company. For instance, the ethics code of the University of Bologna has been recently revised. And as soon as it has been approved, I went straight to the text and I tried to learn it because ethics is really important. And it is, in a way, it is prescriptions by law are important, but also ethical requirements when you work in your workplace are extremely important. For instance, many people don't know that there are ethical codes for the behavior in the social media that we need to observe when we represent institutions. So myself, as a representative, as a professor of the university, I am required to adhere to the ethical code of my job in general and the ethical code of the University of Bologna. So I can't write on the social whatever I want and say, this is just my personal opinion. I'm speaking for myself and it's my personal opinion. No, I mean, when we have a position, and especially a position related to an institutional position, a position related to education, we can't say that we speak at a personal level. I can't say that I am in favor of a crime, but it's just my personal opinion. No, I am an educator and I can't say that, okay? And so this is something that is really important, but this is just a parenthesis, but I wanted to bring this to your attention. Okay, and so basically these are the 4 criteria, and let me introduce the alternatives because then I stop here. So the 3 alternatives are building a dam, reducing losses, for increasing water resources availability. The problem is I need to increase water resources availability, similar as the previous one that I did for InfoGap. So the alternative is building a dam. Here is a picture of the Vaillant Dam. By the way, if you never visited the Vaillant Dam, it deserves a visit. In this season, it's perfect. If you go there, there is a ticket to get in. It's very nice. And studying the history of this dam is really an interesting history, maybe that an interesting story, maybe that you already know it, and there is a lot on the web. On the other hand, if you get an opportunity to go there, as I said, this season is the best one. Okay, so this is the first alternative, but we can increase water resource availability also by reducing losses. There are losses in water supply systems. You may know that Italy has not very good performances in terms of losses. We have losses of about on average, I think 35% in the piped water supply systems and 50% in the irrigation water supply systems. So quite important losses. It means that for irrigation, if we could eliminate the losses, which is impossible, by the way, but we can reduce them. But let's suppose that we could eliminate, then we would get twice the volume of water at the field. So, I mean, it is an important investment, but it costs a lot of money. It's really very costly. Thousands of kilometers of canals to be, fixed. And another opportunity may be to use precise irrigation. Modern irrigation systems allow to save 30–40% of water with respect to traditional systems. These are the three alternatives that have to be decided based on net benefit, environmental impact, impact on river flow regime, and CO2 emissions. And we will discuss this next Monday. And I think we have plenty of time to make it. So once again, next Monday, 9:11, 10:45 lecturing, and then we close with a question and answer session at the end. Coffee, and 11 we go in the lab for about half an hour. Good, thank you very much.